This is EE 619, lecture 8. So we have been dealing with the static characteristics of the CMOS inverter. So in particular, we saw how we can calculate the midpoint voltage of an inverter. And we did this calculation separately for short channel inverters and also for long channel inverters. And what is the conclusion that we got? I can change the value of the midpoint voltage by changing WP by WN. If I increase WP by WN, what happens to the midpoint voltage? It moves closer to VDD, meaning it increases, right? So if I were looking at the VTC characteristics, that is, if I were looking at the V0 versus Vin characteristics, as I increase my WP by WN, the curve is going to shift to the right. And if you decrease your WP by WN, it's going to shift to the left. Then we also did the calculation for the noise margin of the CMOS inverter. So again, we did this for short channel inverter and long channel inverter. What is the conclusion we made for short channel inverters? How do we proceed calculating the noise margin? Yeah, we use a linear piecewise approximation. So if you had a characteristic like that, you will first find out the midpoint voltage. You will find the slope of this curve at that node, and then you will draw a straight line which passes through this midpoint voltage with the corresponding slope. You will also extend the lines corresponding to VOH and VOL. And this gives you now the ideal, this gives you the approximated VTC characteristics. Now from this, you can get VOH, VOL, and what is this voltage? VIL, and finally VIH. So this is the linear piecewise approximation. Now for the long channel transistors, we saw that when the lambda is very, very negligible, at the midpoint voltage, the slope is going to be very high, right? So you will have a curve looking something like this. Now in this case, we found that the equations are simple enough to actually do the calculation. And what was the conclusion we got? So this gain at this node is inversely proportional to lambda n plus mod lambda p. Now, if this lambda n and lambda p are very, very small, the gain here is going to be very close to minus infinity, right? So in this case, we found that the equations were simple enough to actually calculate for VIL and VIH. And the range between VIL and VIH was very small. The transition region was very small. And as your length of the channel increases, we found that your curve VTC is going to look more and more ideal compared to an ideal VTC characteristics. Okay, so now let us make some conclusions about the positive features of a CMOS inverter. The first part is that all the swings are rail to rail. Right? For logic 0, you have the ground supply. For logic 1, it directly corresponds to VDD. VOL is ground and VOH is VDD. Now, does this depend on how you choose the ratios of PMOS and NMOS? No, right? Any confusion here? If I change the ratio of WP and WN, how does the VTC change? Does these values change? No, it simply gets shifted to left or right. So your VOH and VOL are still corresponding to the supply levels, either VDD or 0. So then what should we call this logic? Ratioless, right? The other logic was ratioed. So this is ratioless. So we have ratioless logic. Now the third part is the output impedance at any point under steady state is very low. For example, let's assume that we are talking about an inverter where the input is VDD and the output is 0. So basically the PMOS is off, which means there is no path between VDD to ground, and the NMOS is on, right? And NMOS is on in which region? If the input is VDD and the output is 0, NMOS is on, yeah, and it is on in linear region because the VDS is now equal to 0, right? Which means you can think of this as a resistor of very small value, right? So you basically have a low resistance path to the output. Now the benefit of this is this, right? If due to some reason, some noise gets coupled to the output, let's say through a capacitor or through some high impedance path. So this is a very large R, right? Now, because you have a low impedance path to the ground, any noise that is getting coupled to this node will have a very small magnitude. Is that clear? So because of this, your circuit is more immune to noise that is getting coupled from other nodes. Now, another important factor that we take for granted is the fact that this has zero input current. Okay. Now, what this implies is that we can have infinite fan out for a given inverter. What does fan out mean? Right. So basically, it is the number of gates that you have connected at the output. So if I take an inverter and I connect multiple other gates to the output, the number of such gates that have been connected is called as the fan out of this gate. So fan out is the number of gates connected to the output. Now, if you had used a BJT-based inverter, you know that there will be a base current, right? So it's not necessary that for any inverter architecture, your input current will be 0. So to have a generalized discussion, let me consider that there is some input current II going to all these inverters. Okay. And let's also assume that the current being the maximum current that this inverter can deliver is I0. Now, can you tell me how many number of gates can you connect if II and I0 are given like this? So the number of gates you can connect will be equal to I0 by II. So this is the maximum fan out you can have. Now for CMOS logic, what is II? II is equal to 0. Under DC conditions, it is equal to 0, right? Which means the fan out can now be equal to infinity. And what has been our favorite point so far? What was one of the primary reasons why we moved from the static power is 0, right? The primary reason why the industry moved from NMOS only logic to CMOS logic was that the static power consumption was equal to 0. So like I mentioned, somewhere in 1980s, we made the switch to CMOS logic. And since then, for the past 40 decades or so, CMOS logic has dominated the field of digital IC design. And for very valid reasons, right? It has all these nice features. And even if a new technology has to replace the CMOS logic, it will have to do better than all the features that we have listed here. Okay, so now let us quickly look at how the inverter VTC is going to vary as you change the supply voltage. So let's say when we are operating with a supply of VDD, you had a characteristic like this. Let's say we slowly reduce our VDD to a value smaller than that. How do you think the VTC curve will change? Let's assume all the threshold voltages, VD set, etc. are retained as it is. So it has to start from here, right? And it will end before the next VDD value. So the curve will look something like this. Now it turns out you can keep doing this up to certain values closer to the VTN. And what will happen is, till you reach VTN, as you keep reducing your VDD, what is the one pro that you can quickly tell me? If I reduce VDD, what is one factor that is guaranteed to improve? We are only talking about static properties, right? Power consumption, right? Yeah. So power in general will improve, but in this particular case, it is only dynamic power. You're right. So your power is going to reduce because the VDD is reducing. Power consumption is calculated as VDD into some current. VDD is reducing. Now, when VDD reduces, your VOH is also reducing, which means the voltage applied at the gate of the inverter is reducing. So the gate to source voltage is reducing, which means the current that is being consumed will also reduce. So you have double benefit. So your power consumption is reducing. The other part is that the gain of these regions, the slope of the transition regions is actually improving. So the gain is improving. What do you think will be the cons of this? Reduce noise margin, right? Because your VOH is now smaller. So which means the noise margins will also be smaller. Now earlier, if you were swinging from 0 to 1 volt, and now if you're swinging from 0 to 0.5 volt, the amount of noise you can accommodate and still give a good logic 0 or logic 1 is going to be smaller. So your noise margins are going to reduce. It is inversely, so you can look at the formula and keep reducing VDD and see how the slope is going to improve. But it is also more of a simulation result, right? You can get certain intuitions from the equations, but this has been shown to be true with simulation results, right? Now, another thing that will happen is your VTC will become more and more sensitive to the technology parameters such as VTN and VD Saturn. Minor changes in VTN, your VTC is going to shift a lot, right? And finally, we will see this by the end of this class. Your delays of the inverter are going to worsen. So your propagation delay is going to increase. Now it turns out, even if you reduce your supply lower than VTN, because of subthreshold conduction, you will get curves, VTC curves that looks almost okay. So there are certain applications where if you're not worried about delay, noise margin, etc., you could potentially have digital circuits operating at very small supply voltages. Now the problem is, as you keep reducing it further, at some point, you see that the gain of this transition region will hit unity. Now, if you reduce below that, then you can't really operate inverter chains because there is no regenerative property. So that is like the showstopper. And it has been shown that up to twice of thermal voltage, you can keep reducing VDD and still get reasonable static characteristics. But your delay, etc., are going to worsen a lot. So gain is increasing up to VTN. Now, as you keep reducing further, your gain will also decrease. So now I want to bring out a small difference in definition of VOH. So the definition we are using in class is this. So we have called this as VOH, and this corresponding to input. When you give input as VOH, the output you get is what we called as VOL. And the area where the gain is equal to -1, we marked as VIL. And this node we marked as VIH. Now, an alternate and equally popular definitions is as follows. So instead of calling these nodes as VOL, you find out the point where the gain is equal to -1. Corresponding to that, you have VIL, and the output voltage corresponding to that is called as VOH. Similarly, this will be called as VOL in that definition. So this definition is used in CMOS VLSI design textbook by Westy and Harris. You might also see the same definition being used in some of the lecture videos. Now, for this course, like I mentioned, we will stick to this definition. But if you are referring to additional materials, please keep in mind that differences are possible in the results because of the difference in the definitions. And in general, if you are reading a new material, right, pay attention to the definition that they are using. And if you are making a write-up to be published to a wider public, then you should ideally give the full curve so that they can quickly understand the definitions that you are using. So you give either this curve or this curve with all the values clearly marked on. Then it will cause no more confusion. Okay. Now, an interesting property of this transition region is that the gain there is greater than 1. Can you think of any application to this? Yeah. So what can you do in analog circuits where the gain is greater than 1? You can use it as an amplifier. So now if I take an inverter, right, let's say I bias it somehow to the midpoint voltage and I apply a small swing here. So I'm biasing it to the midpoint voltage, and around this, I'm giving a small swing. Now this corresponds to 2 points here, which means you can get a amplified signal. So inverter-based amplifiers do exist. You can achieve very good gains, but the problem is depending on this width of the transition region, your peak-to-peak signal, the peak-to-peak amplitude of the input signal will be limited. But this is also a common type of amplifiers that are regularly used. Okay. So now with this, we are now in a position to move on to the calculation of propagation delay. But before I do that, let me set some ground rules. Right. So let's say I have a design with 20 inverters. How many independent parameters are there for me to set? W's of all the transistors, right? We are assuming that all the lengths are set to minimum length. So now how many parameters are there? So 20 inverters, each inverter has a PMOS and an NMOS, and you can set the W's of both independently, which means you have 40 bits to set. I think we have already established that a purely mathematical approach is not possible. Right? Because one, if you use the first order models that we have derived, it will not give you sufficient accuracy. So for good accuracy, you will have to deal with the level 54 model. And I think it's fairly reasonable to say that with level 54 model, you will not be able to derive equations to identify what should be the width for 40 different transistors, right? An alternate approach that sometimes people take is what we call as a spice monkey. Have you heard this term before? So have you heard of the story wherein, not the story, the hypothesis that if you take enough monkeys and give them enough typewriters and give them sufficiently long time, you can eventually get the full manuscript of Shakespeare novels, right? So the idea is that if there are enough random events, you can potentially get the complete novel typed out by a monkey. So similarly, if I give you very good powerful machines and enough time, with enough random simulations, you will be able to get a circuit that works, right? But then you are leaving it purely for random chances, and that is not what you should be doing. So what we really want to do is an in-between approach, where you have first order models for quick estimation, but you also utilize the powerful simulation tools and models available to you. So if you are starting out a design in this fashion, even before you run the first simulation, you will have a very good estimate for the W's that you want to use. You will have a good starting point. And then you will also know in which directions you have to move each W, whether to increase it or decrease it. And you'll roughly know the amount by which the change has to be made. And you will also know the pain points or the failure points for the circuit. And as your experience increases, you will be able to predict all of this even before you run your first simulation. And then you will run the simulation and verify your hypothesis. Now, the difference between the Spice Monkey approach and this approach could be anywhere between, let's say you can finish it in half an hour using this method, whereas using the Spice Monkey method, you may take up to 3 months to run all the simulations and get to the optimal point. So the idea of this course is to make sure that you don't go to either of these extremes and you're able to strike a balance so that you get to close your designs as fast as possible. Now, to do this, so in the calculation of the propagation delays, we are going to make a lot of approximations. Now, the idea behind the approximation is this. If you ask me, let's say I have a circuit A and circuit B. If you ask me whether circuit A is going to be 30% faster than circuit B, then I'll be able to give you a fairly correct answer based on the analysis. But if you ask me whether it is going to be 3% faster, I might have opinions based on the analysis, but I'll not make a statement till I verify it using a simulation, right? So that is the whole idea. You are going to get very crude first order results, but that is sufficient to guide you in how to go about the design. Okay. So now with this, let's see how we can calculate the propagation delay. So quickly, if I have a V in that is rising like this, corresponding to that, we'll have a V out which is falling like this. Now, given that our signal is swinging from 0 to VDD, what point should I look here? How do I measure TPHL? Right. So 0 to VDD, what is the 50% point? VDD by 2. So I find out when this is hitting VDD by 2. Then I also find out when this signal hits VDD by 2. And the delay between them is called as propagation delay high to low. High to low because the output is going from high to low. Now, the first approximation we are going to make is that it's too difficult to deal with an input signal that is rising like this. So we'll apply a step input. So we'll apply the step input corresponding to the time t equal to 0. This is going from 0 to VDD. You will have the output falling from VDD to 0. And we'll simply look for the point where this reaches VDD by 2. Right? And the TPHL is now the distance between these two nodes. So the idea that you have to remember here is, in this calculation of TPHL, the gate voltage. What is the gate voltage? Based on the diagram, it is equal to VDD, right? What is the output voltage? It starts from VDD and it goes till VDD by 2. Okay. So this is what you have to remember. Now I had asked you to do the calculation for discharging a capacitor through an NMOS. So the input is as shown here. At t equal to 0, this is going from 0 to VDD. This is my output node V0. And the capacitor VC at 0 minus will have the value VDD. Right? And you are interested in how this V0 is going to discharge from VDD to VDD by 2. And we said that there are two ways in which you can analyze the circuit. The first method is to model this NMOS transistor. So the first method is to model this NMOS transistor as a, what is the first method? So method 1, let's say I am modeling it as a current source. And in method 2, we will model it as a resistance. So did you get a chance to do this? Any comments on the results you got? Did anyone try this? Okay, so let's start with method 2. Okay. So we are going to replace this circuit with an equivalent resistance here, with a resistance and then a capacitance. Now the idea is this: if you have V0 as the voltage here and some current IDS is flowing, I can find out the value of resistance R, for which if I apply V0 here, I will have the same value of IDS, right? But the problem is this: as you change your V0, let's say from V0 to V01, the current value is going to change in a nonlinear fashion, which means your R will have to be replaced by another R1. So you cannot use the same value of R as your V0 is varying from VDD to VDD by 2. Your R has to be a function of V0. And this is not a linear function. If it was a linear function, then there was no problem, right? So now what should we do? We have to approximate. What sort of approximation should we make? So we have to replace this R. We have to make it independent of V0. Okay, how? Right. So we can take the average of the R, or maybe there are calculations where it makes sense to take the maximum or minimum. But as a general rule, taking the average is likely to give you the answer closest to the required answer, right? So now we are going to replace this R with the average value of R as the V0 varies from VDD to VDD by 2. So how do we find the average value? So let me first write the equation for R as a function of V0. What would this be? This will be V0 by IDS. Now to write the expression for IDS, I need to know the region of the NMOS transistor. So what comment can you make about the three parameters? So we have VGS minus VTN, VD sat n, and finally VDS. What is VGS minus VTN? This is VDD minus VTN, right? VD sat n, whatever is the numerical value, you will have that. What about VDS? It will vary from VDD till VDD by 2. This is our region of interest. So if I plot the ID versus VDS curve, you are going to be operating from VDD to some VDD by 2. Right? And if you are assuming a short channel transistor, very high chances that the VD sat n is going to come before this. So I will write the expression for RV0 as V0 by mu n COX W by L into VD sat n into VDD minus VTN minus VD sat n by 2 into 1 plus lambda VDS, which is V0. Okay. So I'm going to write this as V0 divided by, so the initial part of this expression is independent of V0. So we can write it as some I0, which is not a function of V0, into 1 plus lambda V0. Now, another advantage of deriving like this is, even if VD sat n was not the minimum number, let's say it was entering into pinch of saturation instead of velocity saturation, you could finally express your result like this, right? So you can derive the whole expression and then substitute the value of I0 corresponding to pinch of saturation. Okay. So now we have the expression for R of V0. So you have some function f of x. You are interested in its average value as it moves from x1 to x2. How do you find out the average? So you can find the slope between the two and I mean, if you had so many values, right, how would you take the average? You would sum it up and divide by half. So now what should you do? Integrate it, right? So you will integrate f of x. You will move the integration from x1 to x2, then divide it by x2 minus x2. Right? So can you do the same and find out what is the average value of R of V naught? Give it a go. So the value of lambda is very, very small. Therefore, you can write it as 1 minus lambda V naught and ignore the higher order terms. So your V final is VDD by 2 and V initial is VDD. So you'll get minus 1 by VDD by 2. Integration from VDD to VDD by 2. I naught is a constant. I can take it out. Then this is V naught minus lambda V naught square times dV naught. So I have 2 by VDD into I naught. I use a negative sign to flip the integrals, flip the limit. And then you have the expression. So integration of V naught is V naught square by 2. This will give you minus lambda into V naught cube by 3. Now, once you apply the limits, what do you get? So this should give you, this is, okay, you're telling me the final answer. What is the final answer? So this is 3 by 4 VDD by I naught minus 7 by 12 lambda VDD square by I naught. Did everyone get the same result? So let's do a quick sanity check. Can you check if the equation is dimensionally correct? What is the dimension of the first expression? This will be V by I, right? It's in ohms. What about the second portion? That is also in ohms because lambda has a unit of 1 by volt. So dimensionally, this equation is fine. Now it turns out it is much easier to work with an RC circuit when you want to calculate a delay, right? Because once you have a circuit like this, so now you have an R equivalent and a C. What is the value of the time constant? So this is R equivalent into C. Therefore, TPHL will be equal to 0.69 into R equivalent into C. Right? Now, when you finally construct circuits, you will have one inverter driving another inverter where these two inverters are connected by an interconnect. And these interconnects are finally going to get implemented using metal lines with finite width and length. So what that means is you will see some resistance, some capacitance to ground, more resistance, etc. Now, if you can simplify this circuit also in terms of R and C, the whole thing again boils down into an RC network. Right? So you have a higher order RC network, and we'll now learn techniques how to calculate delay in a higher order RC network. But the idea is we can simplify the whole thing into an RC network, and then you just have to deal with R and C in calculating the delay. So it makes it easier to model it using R and C instead of modeling it with a current source and a capacitor. But just to show you that two methods will give you the same result, let us also do the calculation using method 1. And in doing this, for now, I'm going to assume that lambda is equal to 0. So I'm going to compare both the methods with the assumption that lambda is equal to 0. But feel free to do full-blown calculations for this with finite value of lambda. So first, let us calculate. Can you tell me the value of TPHL in method 2 when lambda is equal to 0? So this is equal to 3 by 4 VDD by I naught. Is that all? TPHL, are we missing something? Right. So there is the value that you have given me is only R equivalent. So you will have 0.69 into this value into C. So can you tell me the final value? How much is this? Please do the calculation. It's very close to 0.5. So if you do ln 2, I think it will come as 0.51 something. So it's very close to 0.5 into VDD by I naught into C. All right. Now let us quickly calculate what result you will get if you use a current source. Now here I'm assuming that the lambda value is equal to 0, which means your current is now constant. And again, we are interested in the region where VDS varies from VDD to VDD by 2. So your problem now reduces to a constant current pulling out charges from a capacitor. So then you can directly say the total charge that has been pulled out will be some I naught into delta T, where delta T is the duration for which the charge is getting pulled out. This will be equal to capacitance into delta V, the change in voltage delta V. So now in our case, I naught is equal to TPHL, right? And delta V is equal to VDD by 2. So can you tell me what is the value of TPHL? So you should get 0.5 into VDD by I naught into C. So irrespective of whether you use method 1 or method 2, your TPHL value will come out to be same. So now if I were to plot both the results, right? Now, the moment I assume an RC circuit, we are discharging the capacitor in the order of e power minus t by tau, right? So you'll get an exponential discharge curve like this. Now, if you are pulling out charge using a constant current source, then you will have a curve like this. And both these curves will intersect roughly at VDD by 2. And the delay that you are interested in is this. Now, for all the other values of voltage other than VDD by 2, the result you get when you take method 1 or method 2 is going to be very different. But we are not worried about all those points, right? We are using this model just to calculate the propagation delay, which corresponds to the shift in supply, shift in the output from VDD to VDD by 2. So we have calculated R equivalent as the average value of resistance as your voltage goes from VDD to VDD by 2. And under the same conditions, method 1, where you assume a current source, is also giving you the same result. Is this okay? Any questions on this? So the propagation delay has two terms, right? There is a constant, then the R equivalent, then a C. So we have seen all the information about R equivalent. What comments can you make about C? Where does the C come from? Capacitance at the output. So now let's analyze this capacitance in detail. So this is your input, which is a step input. Here you have the output, and we are assuming some capacitance at this node. So what all capacitances will contribute to this C? So we have to look for capacitances that are connected to this node and some other node, right? So can you shout out all the capacitances? Which gate? Inverter 1 or inverter 2? Inverter 2's gate capacitance. So the total gate capacitance of this, I will call this as CGP. You will also have the total gate capacitance associated with the NMOS. So CGN. What else? Right. So you will have a capacitance from drain to bulk. So CDBN and CDBP. Anything else? Capacitance on the wire. So that will come parallel like this, CP. So you can always add whatever capacitance you calculate from all these transistors, you can add CP to it. So for now, I'm going to assume that CP doesn't exist. Okay, we'll assume ideal interconnect. Is there any other capacitance connected to this node? CGD, right? So you have a CGD connected like this. So CGDP, and you will have a CGDN. So now I can write this total capacitance as a sum of two distinct capacitances. One is the capacitance due to the driver inverter, which I will call as the self capacitance. So this is C self plus any load that is connected to this node, right? So C load, or I can also call it as C fan out. So now even if I didn't connect anything to the output of the first inverter, you would still have some capacitance because of the self capacitance. Now, as you keep adding more inverters, your fan out capacitance or the load capacitance will keep increasing. So now we have to determine the values for C self and C fan out. Let's see how to do that. We can start with the CGD capacitance. So this is at VDD. This is varying from VDD to VDD by 2. What is the region of PMOS? This will be in cutoff. So PMOS is in cutoff. What about NMOS? It will go from saturation to. So it could remain completely in saturation region, or it could potentially go from saturation to linear region. So we are not very sure about it, right? Now for PMOS, if it is in cutoff, what is the value of CGD? Please look at your notes and tell me the answer. Is it 0? So CGD and CGS, it has two components, right? That is the gate to channel capacitance component. Is there something else contributing to CGD and CGS? Overlap capacitance, right? So you will have overlap capacitance, which will be given by COVP into WP, right? What about NMOS? So this is CGDP. Now, if this is in saturation, you would have just the overlap capacitance, right? If it was also entering into linear region, you would have this plus half into COX into WL, right? So a reasonable approximation that we generally make is to approximate CGDN as COV into WL. Only the overlap capacitance is existing. Sorry? So in saturation, this is the capacitance. We are talking about CGDN. So in saturation, this is the capacitance. Now it's also possible that it might enter into linear region by the time it gets to VDD by 2 point. In case it enters the linear region, for a short duration, the capacitance value will be this. But we are going to approximate and say that the capacitance value is equal to COV into WN. Only the overlap capacitance we will account. Now, if you had both the values, then you have to find out the duration for which it is in saturation region, the duration for which it is in linear region, and take the average. But a very good approximation is to simply say that the total CGDN is the overlap capacitance. Okay. So this solves part of our problem. Now we know that the total CGD capacitance is simply the summation of both. So we have now found out a capacitance that lies between the gate and the drain. But what was our aim? We want to transform this into a capacitance that is connected between the drain node and the ground node. Right? So any suggestions on how we can do that? So there are explanations based on Miller compensation, but so the definition of gain is very tricky here, right? You say gain is -1. Why? Because for an inverter, so that is a little tricky. So I'd like to use the explanation where you retain the same change in charge. Okay. So let's go through that definition. So let's say if I look at this inverter, right? As my input goes from 0 to VDD, the output is going from VDD to 0. Right? So what is the change delta V seen across this capacitor? Delta V in this direction. It is twice VDD, right? One node is going from 0 to VDD. The other node is going from VDD to 0. So the total change seen across this capacitor is 2 VDD. So what is the total charge associated with this change in voltage? That will be 2 VDD into CGD. Now I am going to replace this with some capacitance, right? That is connected between this node and the output. So the corresponding change that you see is from VDD to 0, right? So the delta V is now VDD. I want to retain the same delta Q. So what value of capacitance should I use? Twice of CGD, right? So now when I transform this CGD to the output where one node is connected to the drain, the other node is connected to the ground, I will use the value twice of CGD. Okay. Is it clear? Now, what is the other capacitance that we have to take care of in the self-capacitance? The drain to body capacitance. Do you remember let's start with CDBN. Do you remember how to calculate this? So there is the bottom plate capacitance given by Cj into the area of the drain of the NMOS. So Cjn into ADN. Plus you want the sidewall capacitance. So you take the Cj as Wn into the perimeter, right? So let me write it as PDN with the understanding that we are ignoring the side corresponding to the channel. So if you had source and drain, you will take the front side, back side, and this side for calculation of the perimeter. You will ignore the side corresponding to the channel. Okay. So Cjn into ADN plus Cj as Wn into PDN. Now, as your V0 is changing, you know that the values of Cjn and Cj as Wn are going to change. Now, our aim is to replace it with a linear capacitance. And to do that, we will find out what is the average value of the capacitance as your V0 is changing. And then we will represent it by using the capacitance at zero bias. So you'll multiply the capacitance at zero bias with some K equivalent value such that this will give you the average value of CJN during that period. Okay. Similarly, the CJSWN will also get replaced with a proportionality factor into the value of the capacitance under zero bias. Okay. So now can you tell me the expression for the full self capacitance? So it is twice of, we have to multiply the CGD with twice, CVON plus WN plus COVP into WP plus, so CJN ADN plus CJSWN PDN plus CJP ADP plus CJSWP into the perimeter. This is okay? The equation will look big, but the idea is very simple, right? We are dealing with the two gate to drain capacitance that has been transformed such that it can be represented as a capacitance from the drain node to the ground, and the two drain to bulk capacitance. So now we have to calculate the fan out capacitance. So this is equal to CGN plus CGP. So now let us look at the region of operation for the second inverter, right? What region would this PMOS be? So this node is going from VDD to VDD by 2. When it is in VDD, what is the region? This is in cutoff. Cutoff to? What comment can you make about this node? This will be 0 and it will slowly start to rise. It wouldn't even reach VDD by 2. Is that statement okay? Yeah. So this is very close to 0, right? So this will be either in cutoff or it will enter the saturation region. What about NMOS? Corresponding to this node at VDD and this output being 0, what is the region? So this node is 0. So this is in linear region and this may enter into saturation region. May, I'm also not sure, right? And if it enters, then you have to find out the duration for which it is in linear region, saturation region, etc. The drain voltage is very small. Correct. It will remain in linear region. It won't even enter into saturation region, correct? So we'll simply approximate this. This you can actually give me the correct value. What would it be? NMOS is in linear region. What is the total gate capacitance? COX into WN into NL, the LN. 2 times of the overlap capacitance into WN. What about CGP? So we'll also approximate this to be COX WP LP plus 2 times into COVP into WP. Right? So you now know the value of the self capacitance. We have calculated the value of the fan out capacitance. So the total capacitance will now simply be the summation of the self capacitance and the fan out capacitance. So you should be able to calculate this total capacitance value, provided I give you all the technology parameters and CJN and CJSWN with K equivalent and K equivalent to already embedded into these two values. So please go through the notes and ask me if you have any doubts on this. Okay, so the expression for R equivalent, let us quickly analyze how this R equivalent is going to change as you change your W, L, etc. So you got 3/4 VDD by I naught, right? Minus a factor which includes channel length modulation. So for quick analysis, I'm going to ignore the channel length modulation. What is the full expression? 3/4 VDD by, what is the value of the current? Mu n COX W by L into VD sat n into VDD minus VTN minus VD sat n by 2. When I increase the width, what happens to the R equivalent? It decreases, right? If I increase the length, what happens to R equivalent? It increases. Any doubts on this? Everyone is convinced? Okay, good. So now what happens if I increase my VDD? So let's assume that VDD is much greater than VTN plus VD sat n by 2. Okay, so in this case, what happens? Yeah, it remains constant. Right, so if I were to make a plot, so I'm going to plot with TPHL versus VDD because R equivalent and TPHL are proportional to each other. So for large values of VDD, when your VDD is much greater than VTN plus VD sat n by 2, you expect to see it remaining a constant. What happens as you keep reducing VDD? Denominator can go to 0. So R equivalent will increase, right? So let me quickly rewrite this equation. So I divide both numerator and denominator by VDD. So I'll get mu n COX W by L VD sat n into 1 minus VTN minus VD sat n by 2 divided by VDD. So if your VDD is very large, it is 1 minus a negligible factor. It is not going to make any changes, which is why you expect to see your delay to be constant. Now, as your VDD, as this factor becomes a significant portion of 1, you will see that the R equivalent value will increase. Therefore, your delay is also going to increase. So you will see that the delay will slowly start increasing like this. So this was a point that I mentioned in the initial portion of the lecture. As you reduce your VDD, you might have improvement in the slope of the transition region. You will see a reduction in the power, but your delay is going to increase. Right. So what you have to remember is what is the range for which this equation is valid. We have derived this equation assuming velocity saturation. So now as this value approaches closer to VDD, you'll have to go back and check if the assumption that it is completely in velocity saturation is still valid. But it will keep increasing. Then eventually what will happen is maybe instead of velocity saturation, it is hitting pinch of saturation, right? So then you won't have this VDD minus some value. It will enter cutoff. So then the question you have to ask is, if it has entered cutoff, is it ever going to reduce further? You are talking about a capacitor being discharged through an NMOS transistor, assume, right? So if the NMOS transistor is entering cutoff as you reduce VDD, right, then you will have some current due to subthreshold region, but your delay values are going to be very high. And right now we have done all this analysis, assuming there is no subthreshold region. Okay, so then another interesting aspect. So let's say the input we have applied. So far we have been assuming that we are applying sharp step inputs, and corresponding to that, you have an output like this. Now, instead of sharp step input, when I give real inputs with a finite rise time and a finite fall time, you'll see that these are going to increase further. So is there any other artifact that you need to consider? Are we missing something in these plots? So there is a CGD capacitance between the input and the output. Yeah, so you'll see coupling to the output, right? So when you have a falling edge, when you have a rising edge here, your output will momentarily rise because of the coupling between the input and the output. So you'll see something going like this, and then the transistor action will take over, and then it will come down. Similarly, even here, you'll first see a dip, and then it will increase. So if you were to run a simulation, and you see very clean waveforms without these peaking, something has gone wrong in the simulation, or you have not taken care of the CGD capacitance properly. Okay? So you can expect to see these peaking and the dip. Corresponding to that, the delay value is going to increase slightly. Okay, so we can wrap up the class here today. Thank you.